We're ready now to give a definition for the derivative. We're going to start by defining the derivative at a point, then we'll define it as a function. We'll also give an alternative formula for the derivative, which is useful sometimes, and as we go, we'll work examples of all of these. Okay, so in our previous video, we found the slope of the secant line through 2 points, and then we let the limit as the distance along the x-axis between the points went to 0. And we've defined that to be the slope of the tangent line at the point x naught, f of x naught. And then we also understood that to be the slope of the function at that point. And what we will see as we move through the course is that there are many ways to interpret the limit of this difference quotient that we're looking at here. So we're going to define this limit when it exists to be the derivative of the function at a point, and then we'll give a wide variety of interpretations to that quantity. Okay, so here's a formal definition of the derivative at a point. So we say the derivative of a function f at a point x naught, denoted f prime of x naught, is the limit of the difference quotient, provided that limit exists. So let's just highlight this notation real quick. So this is f with a hash mark as a superscript. It's not a 1, it's not an exponent, it's just a single quotation mark. That's our notation, and we'll introduce more notation shortly. There's actually historically many different ways to denote the derivative. So for this definition of the derivative at a point, x naught is some value, right? So maybe we're finding f prime of 5, right? The derivative at 5, or -2. Any value really in the domain of the function. And as long as that limit exists, then that value is the derivative at that point. But it's going to be much more useful for us not to just find the derivative at a point and then another point and then another point, but to define a function whose input is any value in the function's domain and whose output is the derivative at that point, the derivative at x. Now we can define the derivative of the function f with respect to the variable x to be the function f prime, whose value at x, so the output of the function, is the limit of the difference quotient, provided the limit exists. And we'll find this is much more useful to work with because then instead of finding the derivative at each point of the function, we simply find a formula that works for the entire function, and then we can plug in different values of x. So let's do that. Let's work an example of that. Let's find the derivative of the function x squared minus 2x, and then use it to find the derivative at 1 and -3. And when reading that notation, we often say f prime of 1 and f prime of -3. So let's start by stating our definition of the derivative. Make sure you know this definition. Very importantly, it's the limit. Don't forget the limit part of the derivative. It's the limit as h goes to 0 of our difference quotient, f of x plus h minus f of x, all over h. And if you completely blank on that, you can always come up with that difference quotient by finding the slope of a secant line. All right, so let's now use the value of the function that we're given. So we're asked to find this for the function x squared minus 2x. So I'm going to plug x plus h in for each x in my function. So this is x plus h squared minus 2 times x plus h minus, and I'm going to resize there so this fits. Now careful here, you're supposed to subtract f of x, all of f of x. You're supposed to subtract x squared minus 2x. So don't forget the parentheses there. If you don't have the parentheses, you'd be subtracting the first term but adding the second term. So don't forget those very important parentheses there. And then all of that is divided by h. Now you can pause and check for yourself that you would get an indeterminate form at this point if you try to plug in h equals 0. You're going to get 0 over 0. So we're going to need to simplify. All right, so our numerator simplifies quite a bit. A quick note, don't forget to write the limit. You have to continue to write the limit until you take the limit. Otherwise, you won't have a true statement with your equal sign. Right? So let's write out our numerator. We get x squared plus 2 times x times h plus h squared minus 2x minus 2h minus x squared plus 2x all over h. And lots of terms are going to cancel here, right? So our x squared terms cancel. Our negative 2x terms cancel. So let's write what's left. So we have 2xh plus h squared minus 2h all over h. And now notice that every term of the numerator has an h in it, so I can factor that out and cancel with the h in the denominator. And that's going to be the trick for almost all of our polynomials that we work with. And once we've done that, we'll see that we don't have an indeterminate form anymore. So now our function we're taking the limit of is just a polynomial. And so we use our limit laws for polynomials. So just plug in h equals 0. So we get 2x plus 0 minus 2. So we get 2x minus 2. It's been a while since we started what we were doing, but we have shown that f prime, the derivative, equals 2x minus 2. So what have we done? We started with the function x squared minus 2x, and we found that the derivative at any point on that function is given by the formula 2x minus 2. So now we can use that to find f prime of 1 and f prime of negative 3. Okay, so if the derivative is given by 2x minus 2, then f prime of 1 means to evaluate this function at 1. So this is 2 minus 2 equals 0. So the derivative at the point x equals 1 is 0. We'll look at this on a graph in just a second. F prime of negative 3 means I plug in negative 3 for x. And now I get negative 6 minus 2 is negative 8. So the derivative at negative 3 is negative 8. So what does this mean? Well, as I mentioned, there's many different interpretations for the derivative, but in terms of the graph of our function f of x, these values give us the slope of the function at the given points. So let's explore this graph a little bit in Desmos. Let's start with the point x equals 1. Let's sort of zoom in here. So we found that the slope of the function at the point 1, there it is supposed to be 0, right? The slope of the function is 0. And of course that means the slope of the line that is tangent to the function at that point is 0. Well, let's find the equation of that tangent line. Well, to find the equation of any line, we need a point on that line and we need a slope. Well, the point that we have here is 1, negative 1, and our slope is the derivative at the x value, which is 1. And we already found that slope. We computed that previously. It's 0. And now since we have a slope and a point, we use point-slope form. And I won't write it anymore after this time. But we fill in our values. So y minus y1, y minus negative 1, is the slope times x minus x1. And of course the right-hand side is going to go away. And we get y equals negative 1. So this is a horizontal line through negative 1, and that is what our graph is telling us too. So there's our tangent line at y equals negative 1. The slope is 0 because it's a horizontal line. So we can interpret the derivative at x equals 1 being 0 to mean that the slope of the function at that point is 0. So let's see now what the graph is doing at x equals negative 3. We can just sort of move our graph around and zoom in. And notice that if you look at the very bottom of the screen, the x-axis will faintly travel with you so you can keep track of what you're doing as you zoom in and scroll up the x or the y-axis here. So we're at the point negative 3, and there's where it intersects here. Let me bring that down a little bit. All right, so there's the point negative 3, 15. And we can kind of look at what the function is doing. It even kind of looks like a straight line. We've zoomed in so much. So here at the point x equals -3, we can see that our function has a negative slope. So it looks like it's a line going in the negative direction. So let's find the equation of our tangent line and see what it tells us. And this is a good place for you to pause and find the equation of the tangent line for yourself. We've done a few of these now. You should be able to do this. So pause, solve, find the equation of the tangent line, and then check your answer. Okay, so the tangent line passes to the point -3, 15. It has a slope of -8, which is the derivative at -3. And then once we write it in slope-intercept form, we get that y is -x minus 9. Sorry, -8x minus 9. Let's graph that now in Desmos and see if that matches our graph. Okay, so I've zoomed out some so that we can see the tangent line, -8x minus 9. You can see it does cross the y-axis down at -9, and at the point we're interested in, -3, 15, you can see that it is going through that point, and it is approximating the function at that point. So we can continue to zoom in and then sort of recenter our graph and zoom in a little more. And at this point, just with Desmos' technology, the line and the function are indistinguishable. So as we zoom into that point, we can't even tell the difference between which line is the tangent line and which line is the function. Now let me zoom back out, and you can see that as we move away from the point of interest, -3, 15, then we can tell the difference between the curve and the tangent line. But close to the point that we built the tangent line about, the function and the tangent line are very similar. And if you're bothered by the term very similar, I'm glad. You should be. We will talk about what that means and with what degree of closeness they have later in the term. Let's now define an alternative formula for the derivative, which is useful sometimes depending on the function that we're working with. So let's let our point P be defined as a f of a. And if we can think of other points on this curve with x values approaching a, and then of course from either direction, either the left or the right, x values are approaching a, and so the corresponding point Q has coordinates x, f of x. Then we can still define the slope of our secant line to be the change in y over the change in x. And we can take the limit, but now instead of the distance h going to 0, we have x approaching a. And this is another way to define the derivative of f at the point a. And here we're just using a instead of x naught, but it's playing the same role. And we can extend this alternative formula for the derivative to the derivative for a function. So right now it's defined as a derivative for a point, but we can extend it to the derivative for a function in the following way. We're going to introduce a new variable z, and z is going to be x plus h. And since we could rewrite this, just solving for h is z minus x, then we can see that h approaches 0 if and only if, so the left-hand side approaches 0, only if the right-hand side approaches 0, only if z approaches x. So then, using the above alternative formula together with our idea of the derivative of a function, we can say that f prime of x can be written as the limit as z goes to x. So we're replacing h going to 0 with z going to x of f of z minus f of x over z minus x. So it's a little unusual to see this new variable z introduced, but just remember this is still just a change in y over the change in x, and then we're taking the limit as the quantities along the x-axis are getting closer to each other. In just a moment we'll work an example using the alternative form of the derivative, And when we do that, we'll also introduce another interpretation of the derivative. So in order to do that, we're going to need some information first. So let's recall this definition from pre-calculus, and then we'll also introduce a new definition. So recall that when a function gives us the position of an object at time t, then the change in position over the change in time is the average velocity of the object over a time interval. So let's give some notation here. So if our function represents position, it's often denoted s of t. S is just the traditional name for the position function. And then, of course, we use t because it represents time. Then the change in position over the change in time, so that's delta s over delta t. So in general, this quantity represents the average rate of change of the function. The change in the output over the change in the input, the average rate of change. And when that function is position and the input is time, then that can be interpreted as average velocity. And we can spell out what change in s is over the interval a to t. And here we'll just assume that t is a larger number than a, so that we're reading from left to right. But we could switch it around if that wasn't the case. But this would be change in s is s of t minus s of a. And then change in input is just t minus a. And if you'd like to see a graph of that, we can just sketch something real quick. So if this is a and that's t, and then maybe that's our function, right? So that's s of a, that's s of t, and that's our function s. Then you can see that s of t minus s of a is the change in y, and then t minus a is the change in x. Now that's average velocity. What we're going to be interested in calculus is letting t approach a, so that we're able to find the velocity not over an interval, but at a point. And that's what we'll call instantaneous velocity, and that's going to be the derivative at a. So here's that information summarized. So the instantaneous velocity, or we can say just velocity, at time a is the derivative of the position function at a, and is given by the following. So we'll denote it v of a, so the velocity at a is the derivative of the position function at a, so s prime of a. And this is just the limit as t approaches a of, and recognize this as average velocity. So it's just the limit of average velocity to get instantaneous velocity. And we can do that with a lot of things, and as we move through the course we'll take out the word velocity here and here and replace it with different things. So average quantity, take the limit as the necessary inputs approach each other to get instantaneous quantity, right? And so we can substitute velocity with many different quantities, and we'll do that as we move through the course. But we already have two interpretations of this, so obviously we have velocity as one interpretation, but if we don't think of our function as the position function, and instead it's just some general function, then the change in the function over the change in the input, as we mentioned already previously, is the average rate of change. And then if we then take the limit as the change in the input goes to 0, this is instantaneous rate of change. So we have our derivative as the instantaneous rate of change. We'll resize that to fit that in there. The instantaneous rate of change is always an interpretation of the derivative of a function. So that's sort of the standard interpretation. And then when you start to add meaning to the function, add interpretation like position, then the derivative means other things like velocity in this case. So let's work an example of finding both average and instantaneous velocity. And in this example, we'll go ahead and use the alternative form of the definition of the derivative, but we could use either form, it doesn't matter. This example is from OpenStax textbook, which I've mentioned before. It has lots of great problems. If you ever care to check it out, it's free and available at openstax.org. Okay, in this example, we have a lead weight attached to a spring. So if you look at the picture here, there's your lead weight attached to the spring. And the spring is oscillating up and down. Its position at time t with respect to a fixed horizontal line, and that's the red dotted line in the picture, is given by s of t equals sine of t. So we're asked to do two things. We're first asked to use a table of values to estimate the velocity at 0, and then we're asked to check our estimate by finding the derivative at t equals 0. And of course, that's going to be the instantaneous velocity and the exact velocity at 0. Okay, so let's start by estimating v of 0 with a table. So we'll have a table of t values, and the other column of the table will be average velocity, and that is the change in s over the change in t. So our change in s is going to be sine of t minus the sine of 0 over t minus 0. So just to clarify in case that didn't make sense, we're assuming that we have an interval that is 0 up to t, or if we take values less than 0, t to 0, and we're letting t approach 0. So t is going to 0, and we'll use values left and right of 0. And let me erase these intervals here so that we have room to simplify our average velocity expression, because the sine of 0 is 0. So this simplifies to sine of t over t. Let me scoot that over. Okay, so let's take some t values. We can use negative 0.01, negative 0.001, and then on the other side of 0, we'll use the positive values of the same numbers. And feel free to pause here and finish this table yourself. Just use a calculator to find the values of sine of t over t. And make sure whenever you're using a calculator to evaluate sine that you're in radians. Right? So always in calculus, we'll do radians for our trig functions. And we'll revisit that later in the term and say why when we are a little more prepared to do so. Another 9. And this is an even function. Do you see this is an even function? Because sine is an odd function, t is an odd function. It's an odd-powered polynomial that goes to the origin, so their quotient is an even function. I don't need to write these numbers again, but I am missing a 9 here. Not that it's a real big deal. It should be 6 9s there. So for the even value, it's the same. Okay, so that's good. Saves us a little bit of work there. Okay, so there's our table of values. And what we see is that as t is approaching 0 from values less than 0 and approaching from values greater than 0, it looks like our average velocities appear to be approaching 1. Okay, so v of 0 appears to be 1. It's about 1. All right, now let's find the derivative at t equals 0 to see what the exact velocity is at 0. All right, let's find v of 0. So v of 0 is s prime of 0. And here, because we're taking the limit of the formula for average velocity, it is useful to use that alternative form of the definition. So as t goes to 0, we have sine of t minus sine of 0 over t minus 0. And as we noticed before, we can simplify this because sine of 0 is just 0. So we get sine of t over t, and we know this limit. We showed this limit when we did the squeeze theorem. This is 1. And that does it. That shows that the velocity at 0, the instantaneous velocity at the single point 0, is 1. And then what we did first was just using a table to estimate it. So even if you found this first, you might go ahead and use a table to check your work. Okay, so now we have two different ways to find the derivative at a point, two different formulas. It doesn't matter which one you use whichever is convenient for you. And we've also learned an interpretation of the derivative that is not just the slope of the tangent line of the graph. That still holds, of course, but when we give our function a specific interpretation, the derivative also has another interpretation.